हाय प्रवीण।
हाय सर। तो ये वसंत साइड से रो रहा है कि उसे अलग से क्लास चाहिए। यार अलग से क्लास नहीं हो पाएगा क्या? He'll have to manage with the
सब
video.
सब टाइम जोन जो है ना पूरा उससे कॉम्प्लिकेट हो रहा है।
बट वो न्यूयॉर्क जा रहा है, 1 घंटे का आगे पीछे होना चाहिए। पूरा का दिन क्यों आगे पीछे हो रहा है उसका?
नहीं, 3 घंटे का है ना, मेरे यहाँ से 3 घंटे का, राइट? तो अभी उसके यहाँ 1 बजा होगा।
ओके ओके।
और दिस इज ऑफिस टाइमिंग, सो उसको मे बी इसलिए दिक्कत होगी।
So what is the earliest we can start then?
अब उसके हिसाब से तो काफी तुम्हारा एकदम बहुत ही ये हो जाएगा, कॉम्प्लिकेट हो
Okay.
जाएगा।
What time it will be around? कितना टाइम होगा?
लेट्स से 9 बजे ना।
हम्म।
तुम्हारा 6 बजे अगर चालू करना पड़ेगा।
ओके।
6 बजे या। और ये शायद बाकी लोगों को नहीं जमेगा।
नहीं,
शायद आपको भी नहीं
मुझे भी
जमेगा।
नहीं होगा।
हाँ वही।
और अब तो मेरे बहुत ही टाइम जा रहा है बाकी काम में, तो अब क्लास सेपरेट लेना मुश्किल हो जाएगा। ठीक है। सो
आपका
यू
स्टार्टअप कैसे चल रहा है?
स्टार्टअप ठीक है, मतलब
फंडिंग फंडिंग वगैरह का?
फंडिंग वंडिंग का मतलब होप, अच्छा आई एम होपिंग कि सब कुछ ठीक हो जाएगा। इस होप
ओके
में
ओके।
मैं शुरू कर दिया मैंने।
नहीं, सही है सही है।
पैसे आए नहीं है बट
हाँ ठीक है रे, आ जाएंगे।
हाँ आ जाएंगे। तो या सो आई एम इन द फेज ऑफ हायरिंग फ्यू पीपल। इफ यू पीपल इंटरेस्टेड आई कैन गिव यू इंटरव्यूज। यू कैन टेक इंटरव्यूज इफ यू वांट।
ओह ओके।
That will give you one more experience. So do you take interviews for your own
या
company?
I take, like I took one, actually two actually. Yeah, but not after that.
Okay, okay.
Now I am leaving. I am joining new team.
Mm-hmm.
Basically, it's a new company itself.
Okay.
Yeah.
What is the name?
So वोक करके एक VR कंपनी है।
Uh-huh.
इंटेल ने अभी 6 महीने पहले ली, लास्ट दिसंबर, आई थिंक फेब में ली।
So you will be part of this VR company now.
Yeah, but I will be part of Intel, but basically it's a startup. So
हाँ ठीक है. So
85
you
लोग काम
are
करते हैं
working in
उसमें।
VR technology now.
या
सही. Nice.
हाँ ठीक, अच्छी अपॉर्चुनिटी थी, बाकी ऑफर्स थे पर ये अपॉर्चुनिटी अच्छी लगी। और स्टार्टअप का भी फ्लेवर आ जाएगा, ऊपर से इंटेल भी रहेगा नाम।
Yes, yes.
तो
ठीक है. Okay. Nitesh still not there. So did you try implementing the graph?
नो आई डिडंट।
No one?
मतलब कुछ
Subhadeep?
अनकन्वेंशनल लग रहा था जब देख रहा
What?
था। अनकन्वेंशनल मतलब बाकी सब कोडिंग से डिफरेंट है ऐसा लग रहा था।
हाँ तो क्या हो गया? कुछ तो ट्राई किया होगा, कुछ सूडो कोड कुछ तो लिखा होगा। और नहीं लिखा तो व्हाट्सएप पे कुछ डिस्कस तो कर लेते. ओके, नाइस. सो देखो, द थिंग इज, नो वन गो, जितना डीप में हम जा रहे हैं, no one actually goes in that deep. First of all, say, there's all the questions, as I've told you earlier also, all the questions in the graph are generally like, you, as I told you, assume everything already implemented, just tell me how will you do it. So for example, find the diameter of a graph, which means the longest distance between any two vertices. This is a standard question in a graph can be. This is the most standard question, and you'll assume your most of the things and then start writing the first of all, just if you talk about a pseudocode, what we'll do, we'll take one node, we'll go to each neighboring node or each neighboring vertices, and then keep on doing that until and we maintain this visited array. We'll maintain some other array for distance. So we do not. I have seen this mostly. We do not worry a lot about spaces. We do not worry a lot about time. There are multiple problems where it will be an NP hard problem, all those where it's impossible to do even less than exponential time and all. So we'll not worry about using extra spaces. We'll not worry about using time complexity. We'll just worry about are we able to solve the problem or not. So using anything you want, just use anything you want, just solve the problem. That kind of problems you will see mostly into graphs, and no one will be able to ask. Will be ever is going to ask so much of deep question in the graph. But still, and I can't say no one, but most of the interviews, they do not ask deep question into the graph. The mostly question will be very simple. Of this level, will find the longest distance in the graph, or it will be something like, okay, I'll use graph to solve it. Like they'll just give you questions, something like, how will you solve the problem of finding how will you implement this social this graph thing of Facebook graph or LinkedIn second level question. So you just see, okay, I'll use a graph, and in every node I'll store the name of the user, and every edge will, and every adjacent vertex will contain the his first connection. So just this level of question will be there until there is some company there are some company who are directly working only on graph and all those. But I actually, most of the interviews I have given, I have never faced any difficult question into graph, because no one asked me question. But there are tough questions in the graph. I haven't practiced. By the way, I didn't practice them while preparing for interviews. So I won't be doing a lot of questions today. Not in the graph, because it will will be wasting time, which will not be asked. Obviously, there are lots of things to learn, but I would like to take the risk of not learning a lot of graphs, but learning a lot of other questions which will be for sure asked. Okay? But yeah, you should have implemented this for us to for you people only to understand what I'm saying. Every time I say I write a line like for all adjacent vertices, you should be able to imagine those things. If you haven't implemented, that will be again many of the discussion will be like of not much use. Okay. Just a second. Can you see the slide?
Yes.
Yeah. Okay. So we learned about BFS and DFS. We know the implementation of BFS and DFS. So now we'll be doing some of the some application of using BFS and DFS. Okay. So BFS, just to give you a reminder, like what BFS was. So BFS was mostly starting from a source, and then like visit all the next neighbors of that source, and then from there is one distance from the source, and after that all the nodes in the second level of all the neighbors of the neighbors, second neighbors. That is how we implemented our BFS, and that was BFS. The essence of BFS is you start from the source and then go visit all the nodes in the first level, and then visit all the nodes in the second level, like of the source. then visit all the nodes in the third level from that source. So that's what we have to maintain in BFS compared to DFS, where we start from the source and go deeper into one direction until we reach the last node where we cannot go ahead, and then come back and then again go to take the second path and then go deeper in that path. So that is DFS. Okay. Now there are multiple other things you can. Most of the problem will be solved by doing either a BFS or DFS only. Like whenever we try solve one, we'll cover all the nodes into the graph using this BFS and DFS. So first let's take example again. I think we have discussed this shortest path. Okay. So given a graph, you have to find the shortest path between source and destination. Okay, given a graph G. Now you think about the implementation. I am not going to write again everything. This was your task. So given a graph G, you have to find a shortest path between the vertex S and vertex D, destination vertex. Okay. So this is the question, and how would you go about solving this? So, and this is an unweighted graph. Okay, most of the time, if I don't mention anything, it will be unweighted. Okay, unweighted and undirected. If I don't say anything, this automatically means. Okay, unweighted and undirected graph. You have to find a shortest distance between source and given two nodes, given two vertices. To find the shortest. How will you do?
Example.
Yes, tell me.
Example.
So so today I'll just give a problem, and then you have to tell me whether you will do a BFS or DFS, and if BFS and DFS, then how? Okay. So this is the first question. You will do BFS or DFS? Tell me. Shortest path.
DFS.
Yeah,
DFS. Anyone else?
BFS.
All of you saying DFS? Anyone who says BFS or not DFS?
I said BFS.
B for Bombay. Yeah. Okay. So Nitesh, now you're saying DFS. How will you do using DFS?
We need to go to the depth first, right?
Okay.
So we'll just start from source and go till destination.
But then, how will you reach? Like, okay, just tell me like algorithm wise. So you have your DFS code. So where we start from the source, and then you call DFS. So let's try to see the implementation of DFS. Where you do.
PDF method.
What?
It was in PDF.
Okay, yeah, it was in PDF. Okay, so can you see the PDF now?
Yes.
Yeah. So yes. So with DFS, you start from some source, and then you do DFS. You reach all the nodes using DFS. Okay. How will you just tweak this or change this to do your shortest distance? Nitesh?
Yeah, it's thinking.
Mm-hmm.
No, not getting.
Okay. Yeah. So now let's. It will be slightly difficult to do using DFS. So shortest path will be done using a BFS. Okay. So in an unweighted graph, the shortest path is what is the path with least number of edges from S to destination from VS to VD. ठीक है, यही है ना? Shortest path from source to destination is a path in which there is least number of edges. If there is a
Yeah.
draw something, so if there is a no one way to reach from here to here is this, and another way to reach from here to here is this. So shortest path from source to destination this is the path in which there is minimum number of edges. ठीक है? ठीक है?
Yes. Yes.
So now to find that what you simply can do is you just start BFS, and you every time you reach a node, you maintain the number of you remember we maintained this distance in a BFS. We maintained D. Where was that code now? That code will be in some other slide.
Yeah, we maintained D and then color also, whether
Yes.
it's been visited or not.
Yes. Yes. So this D, which we have maintained, this D will be used every time, and we can simply find this shortest path from. The shortest path will be calculated in this one, like that will be the shortest path. This is the shortest distance from source to destination. Whichever is calculated, your D array will give you the shortest distance from source to your whatever vertex you want. This BFS will cover everything, but the moment you fill your D of destination, that is the point you're done. Okay, I have filled my D of destination, and that is the shortest distance, and that path is from where with the path which I traversed. This pi will be used if you want the path. This D will just give you shortest distance. This D will just give you shortest distance from source to destination. Okay, what is this D of S? Not D of S, but D of D array. This D array is the distance of all the vertices from source. Now D of VD was V of destination vertex. That will contain the shortest distance from V of S to V of D. And this pi will help you. Pi will help you find the path. What we are doing which pi of u we are changing pi also. This pi will help you in getting the path. So once you have done the BFS, you will be able to go back using pi. You will be able to get your path as well. Apart from just the distance, shortest distance, you will be able to get your path as well. Whatever path you understand how will you get the path by doing this algorithm. You started from your source. You have done a complete BFS is done. By the way, you don't have to do complete BFS if you're only working for two vertex V of S and V of D. The moment you calculate your pi of VD or D of VD, that moment you just have to stop. But ठीक है, हम पूरा BFS कर लेंगे. The moment you are done with all the BFS, we just check out two things. One is D array, which is distance array. Distance array. What is the distance array of VD? VD is that will give you the shortest distance from source to destination, and pi of VD will give you its parent, and that will give you its parent, and which eventually leads to the root, and that will be the shortest path. Okay? So this BFS we have not made any change. The BFS which I have written here is good enough to solve your complete thing. So the only thing was we'll use BFS to find the shortest path. Okay?
Yes.
Yes. So now next question is, I'm moving ahead. I'm asking some question. How will you detect a cycle in the graph? Do you know what is cycle? Again, I am not.
BFS.
Yes, come again.
BFS.
D or B में confused. Bombay or Delhi?
Bombay FS.
Okay. You're saying you'll do BFS and
Yes. Just visited जो है अगर फिर से वहाँ पे ही चले गया तो
फिर से वहाँ पे चला गया तो
that will be cyclic.
तो वो DFS में भी हो सकता है वो तो
DFS. Yeah.
Subhadeep.
BFS.
Bombay, Delhi.
Delhi.
DFS. I think you were just giving answers randomly without thinking much. So सोच के बताओ. I'll ask how also. Okay, so both of them is good enough. Either you do a BFS or a DFS for a undirected. Okay, I did not say anything. That's why it automatically means undirected and unweighted graph. So what is in a undirected graph? Either you do a BFS or a DFS. Both of them will work. Finding a cycle, if cycle exists or not. Okay. But now the next part of the question is cycle detection in a directed graph. Okay, cycle. I'll draw a graph and I'll tell you whether it's a cycle, whether there is a cycle or not. This is a directed graph. Does it have a cycle?
No.
No. Okay, but if it was an undirected graph,
it's a cycle.
It has a cycle. Okay, so now the next question is, so we are done with the cycle detection in an undirected graph. Now the next question is cycle detection in the directed graph. How will you detect a cycle in the directed graph? Okay, so before we talk about this cycle in a directed graph, which is a very common question again. This is again a question, the common question. So before we do that, I'll try to talk about few terminologies which are here. Yeah. So you can see this is an example of a graph which has one node. This is source node. Then this node. There are 4 nodes, and then one node outside also. Okay, there are not outside, but these are the nodes, and then we can see edges also. We can see all the edges, and we can also see our vertices. There are 5 vertices. 1, 2, 3, 4, 5, 6 vertices. Okay. Now this is a directed graph. We have all the edge with directions also. Okay. So what I want we have colored the. Can you see the colorings? This is a red or what a color. There is a color also. So there's a black edge, there's a red edge or brown red, whatever. There's a green edge, this is a brown green edge, and there's a tree edge. Okay. So but first let's take a forward edge. So what is a forward edge or a tree edge? So when you what is the forward edge? Forward edge, all the edge which are so when you start from a source, so this edge can be decided only when we have decided our source first. Okay, so we have decided this is our source. This is our source. Now after we have decided that this is our source, there are two edges going out of it. One is this and one is this. So we haven't talked about the spanning tree. I mean, we have talked about the spanning tree. So first it has created a spanning tree from this source. So it can visit this node and then this node and this node and then this node. So this will create a tree. Okay, this is a spanning tree or the minimum spanning tree due to minimum number of edges required to cover all the edges. So this edge plus this edge plus this edge and this edge. These four edges will cover these five vertices plus this vertex will have to plus this vertex will have to cover separately. But these four edges is good enough to go through all the vertex. So this is a minimum spanning tree. So all the edges which are part of the minimum spanning tree is called tree edge. Okay? Confusion है यहाँ पे मैं repeat कर रहा हूँ.
इसमें cover नहीं होगा ना 2-3?
2-3
It's a directed graph.
हाँ directed तो है ना. This edge and then this edge. This edge is covering this also ना. 2-3 कुछ और है but हाँ this node if you call it 2-3 ये cover हो गया ना. With this edge, this blue edge, this blue edge, this blue edge and this fourth blue edge. These four blue edges is minimum spanning tree. Just with this four edge, we can cover this vertex, this vertex, this vertex, this vertex, this vertex.
Right.
Whenever we talk about minimum spanning tree or spanning tree, we only talk about connected components. So, if you talk, this is one connected component and this is another connected component. This is not, you cannot go from anywhere to this. You cannot jump back to this. So, when we talk about minimum spanning tree, these four edges is good enough. We don't, even though we are not able to cover this, these are not tree edges. So, this is a tree edge. For this graph, for this connected component, I'm making a circle. Let me just use the pen also. So for this connected component, the minimum spanning tree is this edge, this edge, this edge, and this edge. Okay, all these four edges. So with these four edges, we have created our minimum spanning tree, and hence these edges will be called tree edge. दिखाइए tree edge. Tree edge clear है?
Yes.
Minimum spanning tree.
नहीं, Subhadev, I can't hear you.
Minimum spanning tree. Minimum spanning tree.
What is minimum spanning tree?
Yes.
Your question is what is minimum spanning tree?
Yes. Yes.
Okay. So minimum spanning tree, given a graph, there can be multiple ways to cover each vertex. So this is a node. This is a node. Let's talk about minimum spanning tree in an undirected first, then we'll come to directed also. Okay. So this is a graph. We have undirected edges. So for this tree, a minimum spanning tree, suppose all of them have same weight. Okay, I'm talking about undirected, unweighted. So these definitions change a little bit when we have directed and weighted. So I'm talking about undirected and unweighted. So for this tree, we want to cover all the nodes. So we have this node, we have this node, we have this. I'm trying to draw this thing again. Now to cover all these nodes, so minimum we need some. This edge is required. This edge is required. This edge is also required. This edge is also required, and this edge is also required, and this edge is also required. Now this is a minimum spanning tree of the same graph. I mean, this is a spanning tree by the way. Okay, it might not be minimum, but this is one of the spanning tree. That this tree structure, this is covering all the. Okay, no, this is not a spanning tree. This is sorry, this is a spanning tree, but this is not minimum. This is spanning tree. What is spanning? First of all, the spanning tree is a tree which is covering all the vertices, or a better word would be a subgraph. Okay, a subgraph which is covering all the vertices. So there are multiple edges which are not needed. The multiple edges which are not needed to cover all the vertices. Actually, this is also not a minimum spanning tree. This is just a spanning tree. This is a spanning tree. Why? Because this is covering all the vertices of this main graph. This is a main graph A, and this A dash is having same vertices with the reduced number of edges. We have not included all that. We have removed some edges, and still we are able to cover all the vertices. But this is not a minimum because there is still one edge which is not required. There is still one edge which is not required. Without that also, we will be able to cover our complete tree. And what is that edge? There are multiple edges. We can remove this edge. So let me remove this for you. Hello.
Yeah, got it.
Yes.
Means
Hello.
hello.
Subhadeep.
Yeah, got it. So minimum number of edges required to cover all the vertices.
Yes. So I have deleted that one unnecessary edge. Now this is a minimum spanning tree with the least number of edges. अब इसमें से कोई भी edge हम हटा नहीं सकते हैं. If you remove any edge, then you won't be covering complete graph. Okay?
Got it.
Yeah. So now you know what is minimum spanning tree. With this knowledge of minimum spanning tree, you have to determine what is the tree edge. So this is a minimum spanning tree, and this is a in case of a directed graph or in case of a weighted graph, minimum spanning tree that will be chosen not just the number of edges but also weight of the y2. So suppose I'm talking about a weighted graph now. This is a weight of 1, this is a weight of 2, and this is a weight of 4, this is a weight of 2 and 3 something like that. So what should I choose? Which one should I go for? Tell me.
1 2 2 3.
ये होना सर फायदेमंद है, ये भी अच्छा है. This is 1 2, and then this is again 2, and this is all covered. That's it. Okay, this is a minimum spanning tree and not this. Why? Because this is heavier than 2. If it was unweighted, then both of them would have been minimum spanning. But if it is weighted, so it's better to include the smaller one, which weight 2, rather than bigger one which weight 4. Okay?
Yes.
Got it?
Got it.
So coming back now. So in this tree we have, this is a tree edge, 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 and with the after that whatever other edges is left, and if it is in forward direction. Now what is forward direction? Forward direction is when you are trying to do a DFS. When you are trying to do a DFS, you'll start from this source, and then next vertex you'll visit with this. So this 0 and 9 or any I and comma j is representing the when you reached here first and when you reach the second. Okay, when you reached here first and when you not reached here, when you wait. So 0 pe aaye, and then you went first pe aa gaye, 2 pe aa gaye, and then 3 pe I came out of it, and then 4 pe I went here, and then 5 pe went, 6 came out of it. So this is like when I reached and when I left. Okay, that kind of I comma j. So I reached on 0 at 0 time, and then on time 1 I reached this node, and time 2 I reached here, and I won't go deeper. I'll come back. So time 3 I came back. I'm not coming out of it. I'm going again deeper in time 4, time 5, time 6 here only. So time of arrival and time of departure. So I came back here. I'm departing here from time 7. I came back here. I'm departing at time 8. I came back here. I'm departing at time 9. Now this departure and arrival we have calculated for all the nodes, but with the help of DFS, we have this our departure and arrival time, arrival and departure. So arrived at 0 time and departed at 9 time. Here in this we arrive at 2 and departed at 3 only. So this once we calculated this, and now see this. Once we covered this completely, we had to sorry, we had to do for this also. So this we had to cover separately. I arrived at 10, I left at 11. Okay. So now we have calculated this. Using these, we can talk about our tree edge and tree edge and our forward edge and back edge and everything. So what is the tree edge? Tree edge is do we have a definition for tree edge? Just a minute. So by the way, tree edge is the spanning tree we talked about. Just whatever node was needed, that gave us our tree edge. Now after we have the tree edge, we'll try to find which all are our forward edge and back edge and cross edge. Okay. So what is the forward edge? If you see this arrival at U, an edge UV, an edge UV. So this edge or this edge or this which edge is forward edge? So this edge will be called a forward edge if arrival at U is less than arrival at V, which is correct. Arrival at 0, U, this thing is 0 and this is 9, so this is correct. And departure at U,
0 and 1 check कर रहे थे, I think. Arrival at U is 0 is less than arrival at V.
I'm talking about this green edge. So we were comparing 0 with 4, which is correct.
Yeah.
0 with 4. Okay. And also departure of U9 is more than departure of V7. Hence this is a forward edge. If you talk about this edge, is it correct for this also? 0 and 1 is arrival of U is less than arrival is correct, but departure of U is 9 is more than okay. So
every
all those things are matching here, by the way. So I think with forward edge, forward is the edge. All the forward edge and tree edge, they are like same edges, but spatial of them are tree edges. All of them forward edge, which certify this. All of them are forward edge. It's just that which is also part of minion spanning are called tree edge. Okay, so forward and tree are same only. Forward edge and tree edge is okay. It's like forward edge is superset. Tree edge is only some of them, subset of forward edge. So forward edge is this is certified. Okay. Forward edge we know. Now part of it is tree edge will be called tree edge. Not all of them are tree edge because it's not part of the minion spanning tree. Hence this is not a tree edge. But this is tree edge. All of them are forward edge only. Okay, forward edge is clear. With the help of forward edge, we have this forward edge is a superset. Some of them are tree edge, are called tree edge. Now comes the main other things of back edge. What is back edge? This is a back edge. When you're doing a DFS, if you ever reach a position where you're going back to already visited, then that is a back edge. This is a back edge, and that will help you in doing your main thing we discussed, detecting cycle in a directed graph. So we know what is the back edge now. What is back edge? Back edge is if arrival of U, this is U and this is V. Okay, this is a back edge. What is a U? This is a U. Let me write. So this is U and this is V for this edge. I'm talking about this edge. This is U and this is V. So what is arrival of U is more than arrival of V. Arrival of U is more than arrival of V. So arrival of U is 2, arrival of V is 0, and departure of U is 3, and departure of V is 9. So this is also satisfied here. Hence this is a back edge. So this is from the logic point, mathematical point of view, whatever. But if you simply see the graph, while traversing a graph, if you reach a node and then you find, and then next is already visited, and that is a back edge. That edge is called a back edge, which you don't go through, which you don't explore. If you talk about DFS, when you do DFS, we don't explore this. If you already visited, we just ignore this. We go ahead with the unexplored part. That ignored edge is called the back edge when we ignore this. So what is back edge from at least from both the point of view, from this mathematical logic as well as what actually it means in terms of representation. This is a back edge. Now, with the knowledge of back edge, we can find if a directed graph has cycle or not. So if it has a back edge, we can simply say that it has a cycle in the graph. So So for our using a DFS, we can find that using a DFS we can detect a cycle in a graph. There is one more edge, cross edge left, but before that, so any question with that, what is backend and how are we using that to determine our cycle? Any question?
Praveen, regarding the forward edge,
Yes.
so from 0 to 9, 4 to 7 is forward edge, correct?
0 to 9
4 to
to
7.
4 7
0 to
is a
4.
forward edge. Yes.
And 0 to 9 to 1 to 8 is a forward edge?
Yes, that is also forward edge.
Okay, yeah, got it.
Actually, it's about us defining. No, this, I don't think this is a very standard definition, but with our definition of forward edge and back edge and cross and tree edge, we will continue with this. There is no I don't see this as a very standard definition of a forward edge and tree and all. But we can only clarify here. You can use this everywhere. Keep a forward edge will satisfy this mathematical logic, and the edges, which is also the part of minimum tree. Obviously, it will be only forward edges. Only we'll talk about when we talk about minimum span tree. In that case, those edges will be tree edge as well. So tree edge, if you ignore tree edge, then there are only two edges: forward edge and back edge. Okay. If you ignore your tree edge right now, you only consider forward and back edge. A cycle will be detected if. So we started with find a cycle in a directed graph. Okay. So if you do not want to have coin these terms only, forget about coin these terms. So we'll be able to just use these two terms: forward edge and back edge. Forward edge and back edge. So if it has a back edge, then it has a cycle. Now, just to make more things more clear, like okay, while DFS or while finding minimum tree, there I could have started and gone to this, and I could have started and gone to this, and then done. But this, if you start from here, then you will not be able to cover this this node. If you do a DFS and you start from here to here, then if you start from here to here, then you go here, and then you will not be able to. You'll have to do a DFS from one more source. So if you start from this source, it's better to go from this to this and then do DFS of all of them, and then not to go from here to here. Yes. So just a minute. What I'm trying to say is, with the forward and back edge. So we have our forward edges and back edge defined. Now I want to decide which are my tree edges, which is okay, same as the previous what I said. Tree edge, when you're done with the BFS, then you know your forward edge and back edge, all the things. Whichever edge is part of the spanning tree is also whichever edge is part of the spanning tree is called tree edge, and all of them will be forward only. All of them will be forward edge. So the tree edge is nothing but a forward edge only with a property that this is part of the minimum spanning tree. I'm confusing you, understand? So we have a forward edge, we have a back edge. Now tree edge are those forward edge which is also part of a minimum spanning tree. Is this good enough?
That 10 and 11.
10 and 11, yes.
We are not including into the minimum spanning tree.
No, we are not, because minimum spanning tree, when we only talk about one connected component. So this connected component is only this. This is not a connected component. This is a separate connected component. This is having edges, but we cannot reach from this connected component to this component. So this is other component, and hence we are talking about only this this component.
So cross edge is there. That's why you are ignoring. Yeah.
Now we'll come to cross edge. Yeah, like now what? Now what do we about these edges? So if there's edge from a connected component to another connected component, and I mean since there are two different components, अगर यहाँ से एक वापस edge होता, अगर कहीं यहाँ से एक edge होता, तो ये same ही component होता. अगर edge यहाँ से एक और edge होता यहाँ से यहाँ, तो ये same ही connected component होता, तो उसमें then these edges would not have been part of cross edge. But since there are two different connected components, that the moment we have two different connected components, then if there is a, first of all, even though they are two different, they have edge. अगर edge ही नहीं होता तब तो कोई confusion नहीं होता. अगर यहाँ से यहाँ edge होता ही नहीं, if there was no edge from here to here, if there was no edge from here to here, in that case there are two connected components, and then there is no cross edge. There is no edge between these two graphs, these two components. But we have these two components with an edge. So this from one component to another, there is an edge that is called cross edge. ठीक है?
Okay. This is
Again, who will ask you this? No one will ask you this. No one is going to ask you about any of these. This is just some terminologies, and which we are using. No one even. I don't think anyone asking these kind of. Tell me whether it's asking any question based on type of edges. No one is going to talk about that. So why we talked? Because we wanted to learn about back edges. Rest is all we don't care much. Why we talk, which was just want to understand what is back edge, so that now we can do our definition of this finding cycle into a graph.
So Praveen, I have one question.
Huh?
So these weight will be already given.
What?
The weights, like arrival or departure weights.
No, that's not given. That's something we have talked about. If, in case you want to find, if you have been given, find all the forward edge and back edge. Then, by the way, this is not the way to find your edges. This is not you first find this and then only you can calculate your whether this is. This is one way to just adding like mathematical point to your mathematical constraint to your edges. I know this is a back edge by my other understanding that if there's an edge from a node to a already visited node, if there's a directed edge from a node to a already visited node, then that is a back edge. We know, and we can get from that definition only. We don't have to calculate all these values. But these are just adding more thing to your definition. Okay, you just said that if there's edge from this to this, then that is a back edge. And if there's an edge from one component to another component, that is a cross edge. Okay, or if there is an edge from U to V and which is relevant, then that's a forward edge. Like all those definitions,
Yeah, so
you already know. It's just adding more data points or like mathematical logic to it. Yeah, what is a forward edge? What is a cross edge? I know from my definition. I know I can see the graph and tell you. I don't have to calculate these values specifically. Now coming to your question, will it be given? No, it won't be given. If you have to calculate these values, you'll have to do a DFS. And while doing DFS, you can maintain this arrival array and departure array. So whenever you visit a node first, you just do arrival of that node equal to maintain a time at time t. Every time you go ahead, you increment time and t plus plus. So while every time you visiting, you get arrival of that equal to t, departure of that equal to t plus 1. Sometimes you have to maintain that yourself. It won't be given.
okay. So my another question was, if we keep tracking like arrival and departure on every node, right? So in that way, we can identify whether it's a forward edge or back edge based on these formulas.
Yes.
So even if it is undirected graph, we can easily find the directed, like which side it's going based on this formula. That is correct, right? Or it.
Repeat. I didn't get it. Repeat.
So we will traverse, right? If it is undirected graph and unweighted graph, let's say. And we are traversing and we are just keeping the weight 0 and 9, 1 and 8, the arrival and departure times basically. So in that way we will be able to find the forward edge and back edge just based on the weights, like arrival and departure.
In case
based
of
on this one.
In case of undirected graph.
In case of undirected graph, yes.
You can call again, as I said, you can define your forward edge and back edge, but there is no standard definition of forward edge and all. Especially in an undirected graph, there is nothing called forward edge and all. So if you want to define those things, you can define, but there is no standard definition of these terms.
Okay.
You can define, yes, in your while doing DFS, whichever I visited first, and then after that becomes a forward edge. You can do that.
Based on the source and destination node, we can easily find whether it's a forward or backward edge.
Yes, you can do, but especially in the undirected तो है ही नहीं, बिल्कुल भी नहीं है, क्योंकि nobody
Okay.
has it. Okay. Okay. So coming back to our main question, if DFS has a package, then there is a cycle. If there is no package, then can we guarantee that there is no package, there is no cycle? Can we do that? Guarantee that?
Yes, based on directed graph.
Yes.
Yes, we can. Now we have reached. Okay, I didn't want to discuss, but ठीक है. So there is something called topological sort. This sort is sorting this directed acyclic graph. This term called DAG. I don't know why it's so popular. Simply a directed and acyclic graph. Most of the time, by the way, we try to implement a real life. It will be a directed acyclic graph. I mean, mostly not, if not acyclic, it will be a directed only. Although we have learned a lot about every time we talk about your both directed graph, undirected graph, but most of the problems will solve will be of directed graph, directed, and that too acyclic most of the time. Okay, but okay. I don't understand a lot because why is this term called DAG very much popular? Directed acyclic graph. What is the directed acyclic graph? A graph in which there is no cycle, and obviously it's a directed graph, so it has only directed edges. Okay, it has only directed edges. So actually, it's simpler to solve some problem if it is a directed acyclic graph. Anything you do, like if you have cycles, if you have undirected, things become a little bit complex. Things are all the problems when we go ahead. If it will be easy to solve for a directed acyclic compared to any other option, a cyclic graph or a undirected graph. It will become a little bit complex to solve for those cases rather than solving for directed acyclic graph. Okay? So given a directed acyclic graph, we can order the vertices of this graph so that every edges goes from left to right. So what does this mean? What does this mean? At this edge, when you're starting from the source and we arrange these nodes. So right now, this looks a little bit arranged also, but suppose there was only this. There was not two components. There was only one component. We come to two components also. Suppose there was this component only. Then the order in which they have been kept is something similar to our topological sort also. So first will be this, and then this, and then this, and this. So if you arrange these nodes depending upon their arrival, so first is 0 and 9, that one. Then the second is 1, 8, and then you 2, 3 or whatever it was, and then 4, 7. And then 5, 6. This is all these vertices have been arranged in the order of their arrival time. This sorting is called topological sort. So this is something similar to, if you try to visualize this, so what you do is just hold the source node and hold the last node which you can reach from your source, and then try to stretch it. Stretch करके बिल्कुल linear line में रख दो, like it's like press it and make it a linear line, then that order is called the topological sort. So mostly, okay, do you understand what is topological sort now? Little bit idea समझ कैसे करेंगे बाद में, but can you visualize what is topological sort? I'll try to find some more examples.
Yeah, example.
What?
Example.
Example. Yes. So this is a graph in which 5 is one of the source. From 5 we can reach 2 and 0, and then from 2 we can reach 3, and from 4 we can reach 0 and 1, and from 1 we can reach 3. Now if you try to just stretch this, like 5 को बिल्कुल ऊपर कर दिया and stretch this, how will it look like is 5 will come first and either 2 and 0 will come after that. So 5 and then 2, and then 0, and then 3. This is one topological sort. This from source 5. Then from the other source 4 and 1, it will be 4 and 1. So this has a solution. Just a minute. 5, 4 is together. Topological sort of the following is 5, 4 is in the first part, and then 2, 3 here, and then 1, 0 here. Okay. So just let me think again. Topological sort is while doing a DFS. That is about visualizing. Now I'm talking about the actual code. How do we do topological sort? So while doing a DFS, we start from one source and we do complete DFS. So for 5, we'll go inside it, and then we'll do it for 2, and 2 will do for 3. Done. And 5 will do. Then 5 will do for 0. So 5, 2, 3, 0 is okay. But what about 4 and 1? How come 4 and 1 is not part of that? So just a minute. DFS करने के time पे. DFS करने के time पे. So the implementation of a topological sort is something similar to a DFS. It's just that while visiting all the vertices, I store that into my stack and just pull it out like again. That gives me my topological sort. So how does that work in this case? If I do a DFS from source for all the vertices, I start from one source 5. I did a weave, but that will give me 5, 2, 0, 3, and not 4, 1. Okay, just a minute. So okay, so if it was simple case, then my algorithm which we are going to discuss, the topological sort algorithm, will be okay. But this, how it is making, even my representation will be okay, that I stretch, and this whatever order we get, that is the topological sort. I stretch 5, and so 5 goes 5 and 4 is at the top, but in 0, how come 0 is at the bottommost? Let me just then for sort of following, they can be more than one. Okay, this line I was missing. Then there can be more than one topological sort for a graph. Okay, so I was missing this point here. I was assuming we have to stretch, and then the stretch in a way that your source is at the first, and then the last one is at the end, and in while stretching, whichever way you can see it, that will be your topological sort. That is visualization wise, and apart from visualization wise, you can do your DFS, and while doing DFS, your sorting into arrival will be your sorting all the vertices by the arrival time will give you DFS. So arrival of 5 will be less than arrival of 2, will be less than arrival of 3. So 5, 2, 3 is okay. This will be one order, but where will 0 go? So arrival of 0 will be after arrival of 3. 5, 4, 2, 5, 2, 3, 0. 5, 2, 3, 0. Arrival of 0 will be after 3. But now there is one more DFS. We can start from here. Once we're done with 5, 2, 3, 0. Once we're done with 5, 3, 2, 0. 5, 2, 3, 0. We start from 4, and arrival of that will be less than arrival of. So one of them which I can sense, one of the topological sort which I am going to write can be this also. 5, arrival of 5 will be less than 2, and then 3, and then 0, and then 4 and 1. So this is also a possible. Topological sort. We can write one more topological. We start from 4, we visit 1, then we visit 0, and then we go to. We visit 4, and then we go to 0, and then we go to 1, and then we go to 3, and then we go to 5 and 2. So this is also possible. This is also possible depending on where we started from. But let's come to that complex case of two startings. First, let's do a simple case of only one starting. Okay? So
Praveen,
simple. Yes.
yeah, so in that last, from 4 we are going to 0.
From 4?
We are going to 0.
Yes.
And from 4 we are going to 1 after that.
From 4 we're going to 0, and then from 4 we're going to 1. Yes.
Then how come we are going to 3?
3 we started from. Okay, this is sorry, this is not wrong edge. I thought this is 1 to 3. No, 3 we cannot go from here then. So that is not 3. I thought there's an edge from 1 to 3.
Yeah.
Okay,
If
so
we start from 5,
what?
if we start from 5,
1,
5,
5, and then 5 will come first, and then 2, and then 3, and then 0, or 5 and 0 and 2 and 3. Either of them is a topological sort. So topological sort, as it was written there can be more than one topological sort for a graph. And not talking about the very special case where there are two starting points. Even though there is only one starting point, suppose there was only this part of the graph. Even though there are two topological sorts possible, 5, 2, 3, 0 or 5, 0, 2, 3. From both the, again, how both are possible? From both our definition, not definition, but from both our perspective. One is, if I imagine, how do I stretch this? I stretch this completely, like I hold 5 and I hold the last one and then stretch. Either 0 will come first, 2, or 2 will come first. Like it's like that kind of stretching. So both can happen. 5, 0, 2, 3 also possible. 5, 2, 3, 0 also possible. Now, from your other definition which I have given is while doing DFS, arrival of sort in the way of arrivals. So arrival of 5, and then we can go to either 0 or 2. So if you go to 0, then arrival of 0 will be more than less than arrival of 2. So it will be 5, 0, 2, 3. But if you go to 2 first, in that case it will be 5, 2, 3, and then 0. So both are possible: 5, 2, 3, 0, or 5, 0, 2, 3. Okay, so now that is about, I'm saying even if you had only single starting point, then both of them are possible. Now, if you had an even complex case when there are two starting points, when they get two sources possible, in that case, so for sure, whichever source we start with, that will give you that topological sort. So, दो तो होगा ही होगा for sure. Either you start from 5 or start from 4. So that it will automatically give you at least two. And after that, you have either you go from 4 to 0 or first, or 4 to 1 first. If you go to 4 to 0 first, then it will be 4, 0, 1. If you go to from 4 to 1 first, it will be 4, 1, 0. Both of them are correct topological sort. Do you get that? I'll come to now the code for this. The code for writing the finding the topological sort. Sorry. Okay? Do you understand what is topological sort now? No one?
Yes.
Okay. तो एक हाँ बोल दो मैं समझ जाऊंगा. ठीक है. Now we'll try to write the code for topological sort. So before I start that, I'll go back to my what we were doing. We were trying to first of all, we started with the application of BFS and DFS. We're discussing what can be done through our BFS and what can be done through our DFS. So we decided finding a whether a graph has cycle or not. In undirected, it was easy. In directed, we have to find the back edge, and back edge definition we got, and then after the definition, we are not talking about using, now that we have calculated arrival everywhere, that thing can be used for our topological sort as well. So there can be a question or a very straightforward question: how will you do topological sort? answer is DFS. Now that is a very technical question or technical answer and a very technical question only. But what is this use of this? What is the use of this topological sort? Like what exactly this topological sort is? So this kind of topological sort is mostly used in your life, like where you're scheduling and ordering. So suppose you have some meetings at some given time. So you have your start time of the meeting and then end time of the meeting, and then other meeting start time and end time. So you try to you have to schedule them and with some efficiency and maintain efficiency or not. That kind of places where you have to join. Each meeting will be some node or vertex or edges, and the duration will be edges, something like that. And then scheduling them so that you first one starts. Your meetings have been given start time 11, start time 12, start time 1 o'clock, 2 o'clock, like that. And every all of them have end time as well. So forget about end time right now. Just starting time. How will you arrange them? So the first meeting will be. After every meeting, you can go from that meeting to. So let me just draft the full question only. So there are multiple meetings with start time and end time. Now there are for every meeting it can be overlapping. So by the way, it can be even more complex. But just given there's an array of meetings scheduled. You have to not schedule. There are array of meetings. For each meeting, I have a start time and end time. Tell me how will you schedule it? That's it. That's the question. How will you schedule it? That's the question. Now I don't want to talk everything. So my question is simple question. I have starting time and end time of n meetings. Okay, all these n meetings are kept in an array. I have starting point and end time. Now your question is schedule these meetings. That's it. And you have a single room, only one room to schedule these meetings. So with this constraint, how will you schedule? You have enough things from here. Just try to answer this question now. So Pradeep, there's an array of meetings. Each meeting has a start time and end time. How will you schedule this meeting? And there's only one room. So Pradeep?
Yeah, okay.
Yeah. Others, just think. I have talked everything here. Only thing is you have to think how will you store the data and how will you do whatever you want. The input given is array of meetings. Each meeting has a start time, end time.
Two meetings can also overlap.
What?
Two meetings can also overlap.
Two meetings can overlap, yes.
Tree edge?
What?
Can we use tree edge?
1 minute. Just a minute. My voice is a little bit. Yes, repeat. So, can you repeat once again?
That tree edge thing.
Tree edge. Okay, tree edge thing you're saying. So now that try to think that this is an interview where we haven't talked about anything. This is a fresh interview. Given us array of meetings, how will you schedule the meetings? And each meeting has a start time and end time. You have only one room, and we want to schedule as much meeting as possible, as many meetings as possible. We want to efficiently use the room. So every meeting has different durations. The efficiency means in terms of that there can be two ways we can define efficiency. One is number of meetings. We want to cover maximum number of meetings. Other thing we can do is we want to cover maximum time in the meetings. So let's just talk about maximum number of meetings. Okay.
Because overlapping is allowed.
No, not allowed. If there's overlapping, choose only one of them. Don't choose both of them. If there's overlapping, just you can do only one meeting. You have to ignore other meetings. So I'll repeat the question.
कोई weight भी दिया हुआ है?
Every meeting has a start time and end time, na? So you can.
If you example.
What?
Example.
You tell me na, what part of the question not go. You want example? So there's an array which has this array contains objects, meeting objects. Every meeting object has start time and end time. Start time, end time. Start time, end time. What exactly do you need as example? Do you want me to write 1, 3, 4, 5, 6, 7? What is that example you want?
So 1 is start time and 3 is end time.
What?
1 is start time and 3 is end time.
This is a very trivial statement. Yes. What is the special thing is? Yes. 1 is the start time and 3 is end time. So I'll just add more statements to my question rather than giving example. You have to think about all the cases if you want, and it will be good if you can tell me, is this case also possible? I'll answer those questions, but I'll again make my question very much self-explanatory. So there is an array of size n. Each index contains a meeting object. Each meeting object has a start time and end time. End time will be always more than start time, not even equal. End time will always be more than start time. And what we have to do is you have to schedule as many number of meetings as possible. You have to so there's n meetings. So schedule at least 10 meetings, 4 meetings, 5 meetings, 6 meetings. Schedule as many number of meetings as possible. And why can't we schedule all the meetings? Because there can be 2 meetings scheduled at the same time, or not at the same time, at least schedule at the overlapping time. In that case, choose only one meeting. So which meeting you should choose so that you end up doing maximum number of meetings. Okay, my question is very clear now.
So based on the time of meeting, we can sort first.
First.
Yeah.
Okay.
So let's say there are 2-3 meetings. One is for 1 hour, one is for half an hour, and one is for 15 minutes. So definitely we will try to accumulate maximum number of meetings, right? So we will try to sort it according to the time. Let's say 15-minute meeting will be done first, and then the 30-minute and then the hour meeting.
But that is this decision of doing 30, 15, 30 and half an hour, 1 hour. You will only take that when they are overlapping. If they're not overlapping, they are one after then that condition is not yet problem. Then there is not a problem. Na? What is the problem of why do you want to? So this problem will only happen for the overlapping case. I agree that for overlapping you might want to do that thing, but you have n meetings. So of course you will sort. That I understand.
Based on start time, then we can sort, and then no, actually we don't have to sort. No, sorry.
If we can draw a graph like this.
Yes. So now that you have your meetings, you want to draw a graph from array. You want to come to a graph. Okay. So let's draw a graph in which
Okay. Yeah, in this picture, like so 5 to 0 and 4 to 0. So there 0 is common, like that.
No, wait. So graph you saying. So I have this array. How will you draw the graph? My point is, what will each edge look like in the graph? What will each edge look like in the graph?
It will be forward edge. Like just we solve the forward edge and backward edge formulas, right?
Sorry. Before edge, what will each vertex look like? What will each vertex be? What each vertex will contain?
That timing.
Timing. So can I simply say that each vertex will be a meeting?
Yes.
Okay. Each vertex will be a meeting, and then what edges will represent? So each vertex will represent a meeting,
that,
and what
edges will represent that I'll finish the meeting and go to another meeting.
Okay, so that is I'll just make that same thing clear. Edges will represent that we can do this meeting, and after the meeting we'll do that meeting. Like we can do that meeting. So if a meeting starts from 12 and ends at 1, and the other meeting which starts from 1:30 to 2:30, and then other meeting starts from 3 to 4. So will you have meeting? So there are 3 meetings. Okay, meeting 1 to 12 to 1, meeting 2, 130 to 230, meeting 3, 3 to 4. Okay. Will there be edge from 1 to 2 and 1 to 3 or both of them?
No. Can you give the example? So, promise.
Let me write now. I'll give you example this time. So, meeting 1, 12 to 1. Meeting 2, 2 to 3 suppose. And meeting 3 is 4 to 5. So I have these 3 meetings. So now this is M1. Suppose this is M2. So all my vertices are edges. But this is a very important thing we did. We didn't realize this, but this is very important we did.
So
changing your data from one format to another format and deciding what these values will represent. You have to think very, very much, analyze very properly, and then only convert your data. So we told that, okay, my array contained meetings M1, M2, M3. I just made them as my vertices. Now I'm talking about edges. So this edge, I'll have edges. What this edge will represent? Now you tell me. Yes, go ahead. Subhadeep, will there be edge from M1 to M2?
Yes, M1 to M2. Then
Will there be edge from M1 to M3?
M2 to M3.
And will there be edge from M1 to M3?
No, first I need to complete M3.
Okay. So my point is, we can do that, but my point is, let's have edge here also. Let's have what and then define what edge will mean. Edge means that after I complete this meeting, I can do any meeting. Obviously, it's beneficial to go through this rather than going directly from here to here. Rather than skipping this. But what having it means, if I complete this meeting, I can take. If I do this meeting, if I cover this meeting, I can do both the meeting. So suppose there was another meeting called M4, which was from 12:30 to 1:30. Suppose there was a meeting, and that is M4. Okay, so there won't be any edge from M1 to, because if I do M1, I cannot do M4. So there won't be any edge from M1 to M4. But from M4 to M3, we can have because that meeting is 12:30 to 1:30. So M4 to M2 and M4 to M3, both will have an edge. Why? Because from M4, which was from 12:30 to 1:30, I'm not writing here, 12:30 to 1:30, if I do M1, then I can do M2 and M3, but not M4. If I do M4, then I cannot do M1, but I can do M2 and M3. So, do you get this? So that's what the edge represents. If I do a meeting at this vertex, then there will be edges from that to other vertices only if I can do those meetings. I'm not thinking we have to just go for that path, but we. ठीक है, समझ आ गया? Now with this representation that you have decided this is how I'll represent, with this definition and representation, you have to solve your main problem. You have represented. Now what do you do? Okay, so we are running out of time. I have lots of things to cover. Take this as a question now, that and we'll talk about only questions. I'll give you more questions today because, as I said, most of the questions in your interviews will not be upon the full implementation, but just about solutioning. Okay, I'll do this. That's that. In terms of graph, very few chances are that they will ask you to write the full working code for the graph. But and even if they ask, we'll try to do that. But I want to cover lots of this mapping. Like, okay, this problem I'll solve using graph, and this will become my vertex. This will become my edge. I want to discuss that. Okay, so let's keep this assignment. Let's keep this as assignment 1. SCH schedule meeting. और तुम लोग कर रहे तो हो नहीं तो फिर भी ठीक है. Now I want to cover your there's something called bipartite graph. Why I'm discussing this? Because there's a simple question to detect if a graph is a bipartite or not. Bipartite or not. Okay, just simple. This is a question only. This is both question and a theory. Sometimes people you can take this as a query or as a question. So detect if a graph is bipartite. What does bipartite means? That if you can segregate your vertices, if you can create two partition of vertices and one set contains n nodes and other set contain and other half. Okay, not half but n1 nodes and n2 nodes. So all the nodes can be partitioned into two sets x and y such that there is no edge between the nodes of x within the set. So if this is one set A B C D, another set is E F G, and there's no edge allowed between A B C D among each other, and there's no edge allowed between E F G. So this is a question. Given a graph, you have to tell whether this is a bipartite graph or not. Can we segregate the vertices in such a way that there are two partitions created and there is no edge between the vertices of each partition within the partition? There is no edge between its own set. Can we do that? So now you understand what is bipartite graph from this view and all. What is it? We'll do how to find that. But do you understand what is bipartite?
Yes.
Yes. So think about how will you determine, given a graph, how will you determine if it is a bipartite graph or not?
Praveen,
Yes.
can we say if we start from one vertex and reach end and traversing exactly once every vertex,
I didn't come again.
starting from one vertex and reaching the last vertex by covering all vertex exactly once. So here we are visiting A, E, C, G, B, F, D.
A E C G B F D.
Yeah.
So उससे क्या हो गया?
मतलब सारा वर्टेक्स एक बार विजिट हुआ है
So
and
what?
we have covered all.
So what if there was an edge between B to C? What will happen? A E C A E C G क्या बोला? A E C G B F D. जब जब एक ही साथ cover होगा. What will happen in that case?
अच्छा, so okay, still it is a bipartite graph, right?
This is not bipartite. This is the edge between B and C. This is
Yeah.
not bipartite.
So this will break.
When it will break? When you reach B, what do you do?
Okay.
Like,
Can we say like each vertex will have degree 2 or 1?
degree 2. Now you're a little bit closer, but degree 2 or 1, how will you determine that?
So now B has 3 after you added 1, right? So we can say like it is not bipartite.
Okay, suppose I remove this. Now it is every edge has
1 or 2?
1 or 2. No one has 3.
No.
Is it bipartite?
Yes, it is.
So your statement is wrong. Okay, so now I'll try to give you a hint. So bipartite means when you start from suppose start from a source. Okay, suppose you start from any source. Now all the so first question is again before solve this. My main question was, will you do a BFS or DFS? Okay, ये question पहले ही पूछ लेता हूँ. Will you do a BFS or DFS? What do you think will be more beneficial, BFS or DFS?
BFS.
BFS, see, Bombay, BFS.
Yeah.
So why? Because if you try to think, we want to ensure that there's no edge between two sets within the set. So now how we first have to determine the set only, like which is what set. So if you start from the source, that is part of one set. So A is part of one of the set. I don't know which, but it's part of one set. Now, every edge going out of it will surely, I mean, not every edge, but every adjacent vertices, which is like edge opposite point of all the edges going out of it, will be part of the second set for sure. क्योंकि अगर एक भी है जो कि किसी वो it cannot be in the same set. So every other, suppose there was one more of this, like edge, this, and then this. All of them will be part of the second set. This and this are part of the second set. Now, if you do another level traverse, go ahead one more level. So now all those neighboring will be part of the again same set. So this while solving this, we try to see that okay, we have to discuss about each level. This is something similar to level, which was in the case of BFS. Hence, we'll do a BFS. So we decide यहाँ से हो जाएगा कि we have to do something like BFS. Now, how that BFS only we have to do, but decision of that we'll use BFS will be helpful here rather than DFS. So we are now we decided that we'll do a BFS and not a DFS. So now that I've decided how let's talk about deeper how. So we start from, let's suppose we start from this A and we mark it as set 1. Somewhere we just maintain one more array, okay? Maintain one more array, which is array of array of this, whether this is part of set 1 or set 2. So just right there in first vertex is A. So we have this.
So Praveen, can we say like every other node is a part of another set?
Every
other node, let's say A. A is a part of set X. Then
I have set 1 and set 2. So set 1, suppose part A is part of set 1, and
then E, the next set. That is part 2. Then again E से अगर C में जा रहे हैं तो it will be again part of 1. So 1 2 1 2 1 2 basically.
So 1 2 1 2, yes. So if that is the order we visiting. So A will be part 1. A will be set 1 and E will be set 2. B will be again set 1. This will be set 2. This is what I have to ensure. And how can I do this? While traversing, if I maintain some set, okay, because the moment I visit, I'll be able to, I'll know what set this is part of. This is wrong. This is 2. Okay, I can't read this. So this is not 1. Okay. So while traversing, or to be more specific, while doing a BFS, we will maintain key what is the current set that I'll assign to all that vertex, and then I'll go for all the adjacent vertices by my adjacent method, edge dot all adjacent vertices, and I'll assign all of them as the next set. If it has not been assigned earlier, if it has been assigned, then I'll ensure that this is same what I want to assign. If it has already been assigned something opposite, then at that point we can tell this is not a bipartite. So what I'm saying is we'll do a BFS. We'll try to and how do we do BFS? We first take the source and then we put that into our queue dot enqueue. We enqueue our source, and at that point of time we have our one more array which tells you whether this is what set of. So we have another array, suppose maintain another array called set. So which is first index will tell you, okay, the first vertex is which set. So suppose we represent that set by 1 and -1. Okay, -1 and 1, or white and black. So let's just take a -1 or 1 and do whatever. So in that array will the first vertex is A. So A will become set 1. Now I'll do my q dot dq. I'll take out the first and I'll do for all the edges of that dq element. I'll for all the adjacent vertices, I'll run another loop. I'll run one loop for all those adjacent, and then check if it is already visited. If it is not visited, then good. I'll just mark all of them as one by one. The set of another set, which is suppose -1. I assign them -1, and I'll push them again into my q dot push. So only thing I am doing. So if you remember BFS, what we're doing so many things. D of u, or pi of u, or color of u. Color was visited. So we have one more thing, set of u. Suppose set of u. So that will contain either 1 or -1. So that set of u will calculate, and that calculation will again I'll repeat what set of u will check. Is this -1 or 1, or set 1 or set 2, or if it is null? Null means it has not been assigned yet. If it assigned something, if not assigned, good. I'll assign it set of that u or set of that v will be equal to whatever current I want to assign. If it is already assigned, if it is opposite to what I want to assign, that point of view just return false. It's not bipartite. Otherwise, we keep on keep on doing our BFS. Do you understand what I just said in my words? Shall I repeat? Because you'll have to write the code for this. Pseudocode only, but you'll have to write the code. If you want, I can repeat, but you'll have to write the code.
If you can repeat.
What?
If you can repeat.
Yeah. So if you remember your BFS, in your BFS, what you used to do was, I'll open the slide for BFS once again. Just a second. Yeah. So in your BFS, whenever you took the head element of the queue, and then for all the adjacent vertices, you decide your color, distance, pi. One more thing you decide, set of v. And that set of v here will depend on few things. Sorry. Will first of all, is it already set of v is null or not? If it is not null, then what is it? Is it 1 or -1? Is it white or black? So let's finalize. I don't want to confuse again. So let's finalize. We are storing either 0 or -1 or 1. 0 means it has not been assigned any set. 1 means it is set one set, or -1 means other set. Okay. So now if I check set of v, is it 0 or not? If it's not 0, then is it 1 or -1? So while like 1 or -1, we also have maintained one more thing. Like we will maintain one more thing. Like we'll change in our method, the BFS method, whenever we DQ something, we'll have to decide what is the color of that. And it has to be opposite. So somewhere here, before we start this loop, here we'll have to set our current color or current, not color, but current set. Sorry, again, we'll have to set your current set. What is the current? That current set will change whenever we start this for loop. Whenever we DQ, we have to change. So somewhere you have to implement that. My point is, before we run this loop, we'll have to set what is current color, and then here we'll check if why I'm confusing color every time. Set of view. Okay, we have to decide what is all of them set should be. That current set you determine here, somewhere here, current set, and then you just check set of V. If not equal to 0, then is it equal to what I want to assign, what this current set is? If it is, then okay, go ahead, don't do anything. If it is not, then return false. Or if it is 0, then just make set of that V equal to current set, which I want to assign. Confused?
No, this one is fine.
Clear? So somewhere here we'll have to set before we go in this loop. Okay?
Okay.
Okay. So now you have to implement this as well. Your bipartite. I'm not expecting a full running code. I'm only expecting with this definition, with this BFS or any other BFS you implement yourselves. You just have to do your pseudocode for this bipartite. Okay? Okay. So we have, yes. So we have covered topological sort. We have covered DAG, directed acyclic graph. We have talked about topological and its usage one place. Then we talked about we haven't talked about vertex connectivity. We'll talk about this edge connectivity and vertex connectivity also. Then that is about, okay, so few more places where we use our DFS is still remaining. This 28th slide, then 29th slide. Bipartite we have covered. Diameter of a graph, which is same as longest distance or diameter of graph. Then we have covered the shortest, but we have only done only for unweighted. Okay, we will cover, this is not assignment, we will cover shortest for weighted, which is very popular algorithm called shortest path for a what?
Dijkstra algorithm.
Yeah, Dijkstra algorithm. Yes, we'll cover that. Then we have, what else is left? Diameter is there. Yeah. So yes, that's almost all of the theory is done. We can just take questions from Geeks for Geeks in the next class. Apart from these assignments, which you have to write pseudocode for sure. Then only I'll be able to discuss, because I'll take another questions. I will discuss myself only Dijkstra and nothing else. All the assignment you have to try, and all these three include your BFS and DFS only. You just have to tweak your BFS and DFS to solve these three. Apart from that, this one Dijkstra I'll take. This is very important, because most of the people, if you ask, they ask this only, and this can be used multiple places. You just have to tell, because they will ask you a question, and then you say, okay, I'll create a graph, and then my Dijkstra will solve the problem. Then they might ask, okay, can you implement Dijkstra? That's why I'm teaching this. Otherwise, no one will likely ask you to write a code for Dijkstra or anyways. But there might be people then, once you give a solution, okay, I'll use Dijkstra, then we'll okay, implement Dijkstra. How will you implement Dijkstra? But so I'll just discuss this. But apart from that, these three things you have to come up. Then only I'll discuss this. In the next class, I'll take more questions on graphs, and that will be the last lecture of the graph. ठीक है?
Praveen, I sent one input for scheduling meeting.
You sent what in chat?
Yeah. That will be the or schedule meeting.
Okay. What do I do with this?
Yeah, for schedule meeting, this is the input. Right?
Come again, I didn't get you. For schedule meeting, what?
This will be the input.
This will be the entry.
Input.
Input. Yeah, this is one of the input you can say. 12 to 1, 1 to 130, 2 to 3, or not necessarily. I mean, yes, this is one of the input, but don't have to assume that they are all sorted initially only. I mean, I just gave you n meetings initially. Like you can have 4 or 5 first, and 12 come on later also. You have given a very specific input which is already sorted, but I'm saying I have any just random meeting. I don't care about already sorted. Okay?
I have to find the maximum meeting. I can schedule.
You have to
find maximum meeting. I can schedule.
Yeah, maximum meeting you can schedule. Yes. Okay. This is a standard question, by the way. Scheduling meeting is a standard question. People do end up asking, and then the answer is I have already discussed in the class. And again, if you just say that much, no one is going to ask you to implement. But if you can write Sudoku, that will be better. Okay. Okay, then I am ending the class here now.
Thank you.
Praveen, one thing. That Prince and Kruskal's algorithm that is required.
Prince and Kruskal's. Okay. I'll do that also. Then I'll cover your Prince and Kruskal as well. That is one of the. By the way, I wanted to cover that into. I'm not both of them. I had planned for Kruskal in my only the algorithm class where we'll discuss about algorithms. But yeah, this we can cover here also. Prince and Kruskal. So I had planned for Kruskal later in only the algorithm class. But yeah, we can cover here also. Okay?
Okay.
Yeah, I'll discuss this. Don't worry.
Okay.
Someone left?
No.
चल ठीक है सब लोग जज करो चलो ठीक है try to do assignment okay
yeah
okay
okay,
bye bye